In today's lesson, we're going to be looking at factoring and solving polynomial equations. So we've already gone through the techniques of sum and difference of cubes, synthetic division, factor by grouping, and now we're going to take a look at just factoring and solving polynomial equations using those techniques. Those of you who need a review on those lessons, see my playlist linked in the top right. So for the first question here, again, when you're looking to factor now, we're just looking to factor this polynomial equation. What you want to look for first is the following polynomial have a GCF? So greatest common factor. Quick check here, we can see we don't have a greatest common factor. So then you move on to your next techniques here. I see a cubic here, but I don't really see that going on in the rest of the expression. I can't see another term I can write as a power of 3. Moving on though, we do have the technique of factor by grouping. Now taking a look here, I can factor out an x squared out of this term, but I'm not going to get an x minus 4 here. So in this case here, what we want to do is we want to try to find a root of our polynomial. What I'm going to do is I'm going to see whether the polynomial at 1 is a root. So using synthetic division, we're going to examine the polynomial at 1 and see whether that yields a remainder of 0. So writing down the coefficients of our polynomial, we have 1, -4, 1, and 6. Drop down that 1. Again, the operation is always addition, so 1 times 1 is 1. Adding, we get -3. Multiplying, we get -3. Adding, we get -2. And multiplying, we get -2. Adding, we get 4. So it turns out that 1 is not a root of this polynomial. Let's try -1. So if I do synthetic division at -1 here and evaluate this polynomial, we get, evaluating the polynomial at -1, we see using synthetic division we have a remainder of 0. Therefore, this polynomial will break up into x plus 1, that's our divisor, and then it's going to leave us with a quotient here of x squared minus 5x plus 6. And continuing on here, once you have a degree 2 polynomial, we can quickly factor this using product sum as x minus 3, x minus 2. So our following degree 3 polynomial here factors into x plus 1 times x minus 3 times x minus 2. Let's take a look at another example. In the next example here, same idea. You always want to look to see whether you do have a GCF. Looking here, I do not see a GCF present. I don't see a difference of squares. I don't see sum or difference of cubes. So once again, I'm going to try synthetic division on this. You'll notice one observation here. This is all summation here. So if I input any positive real number, it's not going to result in the polynomial equaling 0. So therefore, if this polynomial has a root, the polynomial must have a negative root. So let's go ahead and try -1 first. Doing synthetic division, we get, trying synthetic division on -1, we see we do not get a remainder equal to 0. So let's try again. We're going to try -2 now. And we see here quite quickly, if I try synthetic division at -2, we end up getting a root of 0. So therefore, this polynomial has a root at -2, and therefore will decompose into x plus 2 times, we go to our quotient. Our quotient now will be x squared plus 6x plus 9. And now we have to examine, can we factor this any further? With quick observation, we can see here that x squared plus 6x plus 9 will factor into x plus 3 times x plus 3. So our polynomial of degree 3 will factor into x plus 2 times x plus 3 quantity squared. So again, just to remind you here, you notice here we couldn't do the sum or difference of cubes, difference of squares, GCF, factor by grouping wasn't working, so I went on to say, okay, let's try to find a root of the polynomial. I ignored positive roots because we were adding all these terms together. So there was no way to input a negative real number that would result in this being 0. So then I just went arbitrarily, started at -1, -2, and I would have kept going hoping to find a root. Luckily, we found the root of -2, and that allowed me to decompose the polynomial into a degree 2 polynomial, and then it just becomes a simple factoring technique to get you there. Let's try another example. The next example here, again, we want to look for a GCF here. One technique you want to do is whenever you see a minus sign as a leading coefficient, you want to factor that out. So let's go ahead and do that. So we'll factor this out first, and then we kind of focus on inside here. Now I'm going to go ahead here and notice that if I take these first two terms and do a GCF on these, take the next two terms and do a GCF on these, we will get the following. You'll notice here that we end up getting factor by grouping as a technique that works here. We end up getting a factor of x minus 2 in both of these. Here I factored out a 3x squared. Here I factored out a -7. Now we can go ahead and collect these together. We end up getting, again, factor out that common factor of x minus 2. We end up getting x minus 2 here, and then we're left with 3x squared minus 7 going in this term here. Continuing on here, you might notice that I can actually factor a difference of squares on this. Let's take a look at decomposing this off to the side. Notice here I can take 3x squared minus 7 and write it as a power of 2 and a power of 2, and now we have difference of squares. Using difference of squares, we end up getting this decomposing as the root of 3x minus root 7 times the root of 3x plus root 7. Summing this into our equation we get, and now you'll see here our degree 3 polynomial factors as follows. Let's take a look at another example. In the next example here, we want to factor this. You can see here that a sum of cubes would apply, so I'm going to go ahead and write this as a power of 3. Writing this as a power of 3, I can rewrite 3 cubed is 27, and obviously x to the power of 3 gives us our x cubed here. Plus, I'll rewrite the 1 as 1 cubed, and we can apply our sum of cubes formula, and it will decompose as follows. Decomposing, you can see here that this takes the place of my x, and this takes the place of my y, so this becomes x plus y times x squared minus xy plus y squared. And again, to remind you, we have our difference of cubes formula, and I'm just letting the x and y be placeholders and just substituting those placeholders into these locations. Let's take a look at another example. Once again, we can factor this using difference of cubes. Looking here, you always want to look to see whether you have a GCF. We have a GCF of 5 here, so I'm going to factor a 5 out first. Doing so, we get, you'll see here, factoring out that 5, we get 125x cubed minus 8. Again, I'm going to rewrite this as a power of 3 and rewrite this as a power of 3. Doing so, we get, and you can see here you get 5x quantity cubed minus 2 cubed. Now we can go ahead and apply our difference of cubes formula, and we get, and now our quadratic is fully factored. Notice here that your degree 2 polynomial has a discriminant equal to negative 300 and therefore has no further roots. Let's take a look at another example. So in the next example here, we want to take a look at this degree 4 polynomial. If we want to go ahead and factor this here, you'll notice there's no GCF, sum or difference of cubes, factor by grouping, nothing of this sort. But you'll notice it does look a lot like a quadratic, except for this is to the power of 4 and this is to the power of 2. So what we're going to do here is we're going to go ahead and do a substitution. I'm going to let t equal x to the power of 2. Subbing this in here, we end up getting t squared minus 2t plus 1. And you'll notice here, t squared minus 2t plus 1, if you were given this question on its own, will quickly factor into t minus 1 quantity squared. But again, we want to factor in terms of x, not in terms of t. So let's get rid of that t and put those x's back in there. So this becomes x squared minus 1 squared. And now you can see here we have a difference of squares inside the brackets. So we can factor this again. This becomes x minus 1, x plus 1, the entire expression squared. And distributing that power of 2, we get x minus 1 squared times x plus 1 squared. So therefore, our degree 4 polynomial will factor into x minus 1 quantity squared times x plus 1 quantity squared. So again, this is the technique of substitution. You'll see here, using substitution, you just let t equal, in this case, x squared, and you've created yourself a quadratic. And then you treat it like a quadratic. Then when you're done, you substitute the t value for x squared back again. Let's take a look at another example. In the next example, it's the same idea. We have a degree 4 polynomial, but it's in the same structure as a quadratic. It looks a lot like 4t squared plus 11t minus 3. So let's go ahead and factor this as if it was this degree 2 polynomial. Doing so, we can do charting or decomposition here. I'm going to go ahead and do decomposition. So using decomposition, we get, again, going through the process of decomposition, we end up getting that the polynomial 4t squared plus 11t minus 3 factors into t plus 3 times 4t minus 1. Now the only thing we have to do here is do our substitution. Well, it wasn't a t, it was actually a y squared. Subbing this back in, we get, once again here, y squared plus 3. There's nothing more we can do with that. We can't break this up anymore. However, we have now a difference of squares here that we can do. Breaking this up using difference of squares, we get, and you'll notice here our degree 4 polynomial, 4y to the power of 4 plus 11y squared minus 3 will factor into y squared plus 3 times 2y minus 1 times 2y plus 1. So once again here, when you're going through this problem here, it's the same idea as the previous example here. You do that substitution, treat it like a quadratic, factor it like you would normal quadratic, and then substitute in that t value. In this case here, t was y squared. And then you look to see if there's more to do, in which case there was. We had a difference of squares I could apply here, and now we are done. Let's take a look at another example. In the next example here, it's the same idea. We have a polynomial that is of the form of a quadratic. In this case here, it looks a lot like 5t squared plus 20t plus 5. So let's go ahead and focus our attention on factoring this first. Factoring this first here, we see we have a GCF of 5, so I'm going to factor out that 5. We get t squared plus 4t plus 3. And a simple factoring technique here, you see a product sum. This will factor into t plus 3 times t plus 1. Now, what did we let t equal? Well, we let t equal 1 minus p. So I'm going to go ahead and substitute that in here. In doing so, we get 5 times 1 minus p plus 3 times 1 minus p plus 1. And simplifying this, we get, and therefore our degree 2 polynomial will factor as follows. So again, that's 3 examples of using this idea of substitution. And the main technique is to treat it as if it was a quadratic, something that you're familiar with. Do all your normal factoring techniques, break it down as you would normally, and then substitute in what that value was, like what t was equal to. In the previous 2 examples, they were equal to y squared and x squared, respectively, and now t was equal to 1 minus p. Let's take a look at the next example. In the next example here, we want to factor this degree 4 polynomial. Again, GCF is something you should always look for. And I can see here right away, I have a GCF of x. So factoring out that x we get the following degree 3 polynomial. I'm going to go ahead and I don't see factor by grouping working, but I'm going to try synthetic division on this. Let's try synthetic division at 1. Trying synthetic division at 1 we get. I actually went ahead and did synthetic division at 1 and 2. Doing synthetic division at 1, we did not get a remainder of 0, so I continued. At 2, though, we did get a remainder of 0, so therefore this degree 4 polynomial will break up into x times x minus 2, and then our quotient here will be x squared minus 3x minus 4. And again, this factors quite nicely. You can see here that this will factor into x minus 4 times x plus 1. So therefore, our degree 4 polynomial factors as follows. Let's take a look at another example. Moving on to the next examples here, now we're looking at solving polynomial equations. It's essentially the same idea, you just have the next step of finding the roots afterwards. So in this example here, step number 1 is you want to bring everything to one side of your equation. Doing so, we get. I'm also going to want to go ahead and anytime you have a leading coefficient, because normally we would factor out the minus sign, because we have an equation, we're going to go ahead and multiply across by minus 1. Doing so, we get. Now, once again here, I'm left with the situation where I want to find the roots of this polynomial. I do not see factor by grouping, sum and difference of cubes, difference of squares working here. I'm going to try synthetic division again on this. Trying synthetic division on 1, we get. So going ahead and doing synthetic division, I tried it at 1 with no luck, tried it at minus 1 with no luck, tried it at 2 with no luck, and also tried it at minus 2 again with no luck. Finally, I got to a root of 3. So I tried it at 3, I got a remainder of 0. Now that I found the root of this polynomial at 3, we can now decompose this into a degree 1 polynomial and a degree 2 polynomial, and it becomes much easier to factor. Let's go ahead and do that. Factoring this, we get x minus 3 times x squared minus x minus 1. Now, a quick check on this here, you'll see that this requires the quadratic equation to factor. Okay, so now you'll notice that our polynomial is now equal to 0, whereas before we would be done, we would just sort of be dealing with the left-hand side that I've written out here. But now, because it's equal to 0, we have 2 options. Either this polynomial is 0, or this polynomial is 0. That's the only way for the product of 2 expressions to be 0, is either one of these must be 0. So therefore, x minus 3 must equal 0, or x squared minus x minus 1 equals 0. Solving for x here, we get x equals to 3 as one possible root of our polynomial. You'll notice here to solve this quadratic equation here, if I do a quick discriminant check on this quadratic, we get, notice if I do a quick discriminant check on this quadratic, we get a discriminant of 5. So therefore this quadratic has irrational roots, and we're going to have to use the quadratic equation to solve. Solving here, we get x equals 1 plus or minus the square root of 5 over 2. So therefore our degree 3 polynomial has the following 3 roots, root of 3 and a root of 1 plus or minus root 5 over 2. Let's take a look at some more examples. In the next example here, we want to solve the following polynomial equation. Step number 1 is to expand and bring everything to one side. Doing so, we get 2x to the 4th minus 4x cubed minus x squared minus 2x. And again, I just distributed the leading coefficients here into our binomials, expanded, brought everything to one side, and we're ending up with this. I'm going to go ahead and factor 2x cubed out of here and a negative x out of here. Doing so, we get. You notice here we have a common factor of x minus 2 in both of these terms. Now, completing our factor by grouping, we get. And you'll notice here we can go ahead and factor an x out of our term here. Doing so gives us. And then we can go ahead and do a difference of squares here. And now we want to go ahead and solve the following polynomial equation. Again, we have the product of three expressions is equal to 0. So the only way that can happen is if at least one of these is 0. So doing so, we have the following three equations. So we can see here one possible root is x equals 0. Another possible root here, if we take a look here, solving for x, we get 2x squared is 1, in which case x is plus or minus 1 over root 2. And lastly, here we get x equals 2. So the following polynomial equation of degree 4 has x equals 0, plus or minus 1 over root 2, and 2 as its roots. Let's take a look at another example. In the next equation here, we want to solve this degree 4 polynomial. So again, technique is always to bring everything to one side. So let's go ahead and do that. After you bring everything to one side, the first thing you always want to look for is a GCF. I have a GCF of x here, so I'm going to factor out that x. And you'll notice here you're left with a difference of cubes inside the brackets. So rewriting these as powers of 3 we get. And I'm going to go ahead and apply my difference of cubes formula. So we get x cubed times 2x minus 1 times 4x squared plus 2x plus 1 equals 0. So again, solving for this here, either the x cubed is 0, which implies that x must be 0, or the 2x minus 1 equals 0, which implies that x is a half. And lastly, the 4x squared plus 2x plus 1 must equal 0. However, if you do a quick discriminant check on this, we end up getting a discriminant that is less than 0, and therefore this has no real roots. So the only two roots of this polynomial equation are going to be 0 and 1/2. So the degree 4 polynomial has real roots at 0 and 1/2. Let's take a look at another example. In the next example here, we've taken a look at this factoring technique. Again, this resembles a quadratic, and if this was a quadratic of the form t squared minus 7t plus 12, this would factor as t minus 4 times t minus 3 equaling 0. And you have two answers here. Either the t value is 3 or 4. But again, it's not a t. It's an x squared. That's what we let t equal here. So in this case here, you're going to have either x squared equals 3 or x squared equals 4, in which case x is going to be plus or minus root 3, or x is plus or minus 2. So the following degree 4 polynomial has roots at plus or minus root 3, or plus or minus 2. That concludes today's lesson on solving polynomial equations. Thank you.